I'm Bishoy Bah, and I've been working with Dana Weinstein and Luca Daniel for several years now at MIT. So today I will talk about the optimization of unreleased CMOS-MEMS resonators. And basically, the outline of my talk, I will first start by introducing what are these unreleased RBTs, and we will get a quick hint about the phononic waveguides in CMOS. I will focus after that on the numerical optimization. How can we optimize such complicated structures numerically through FEM simulation and by the help of model order reduction and memoization. And finally, I will demonstrate prototype in IBM 32 nanometer SOI with very exciting results. So first, what are unreleased CMOS resonant body transistors, or RBTs? These are truly solid state MEMS resonators. They are completely embedded inside the CMOS die, fabricated in the regular CMOS process, just like any other transistor or circuit. They don't need any post-processing. There is no release steps. There is no back etching, nothing. It's a completely solid state device. And so this, of course, allows to minimize the parasitics in routing to nearby circuits. And it also gives us access to the high quality materials available in the CMOS process, especially the silicon substrate and the polysilicon layer. So also with this, we have access to the low or the small feature size provided by the CMOS technology, which allows us to easily scale to gigahertz frequency while hopefully achieving a high quality factor. So why do we care about these devices? I guess by now you have heard enough motivation for high Q resonators and for miniaturization and integration. So our goal is basically to target applications that require ultra compact form factor and very low power, such as wearable electronics, medical implants, autonomous wireless sensors, you name it. It all now needs these resonators. So let's quickly start back 2 years ago at IFCS. I introduced this unreleased RBT structure, and it basically relied on a phononic crystal, as you can see here in this cross section, patterned from the copper metal layers and the low K dielectric of the CMOS process. And this phononic crystal back at the time achieved 85% fractional band gap. It was the first demonstration of a phononic crystal inside CMOS technology. And underneath this phononic crystal, we have here basically our resonant cavity. And in this resonant cavity, we have two MOS caps used for electrostatic actuation of the resonator. And we have in the middle a single MOSFET that's used for piezoresistive sensing. And this device achieved a quality factor of 252 at 2.8 gigahertz. And you can see here the stress distribution of the vibrational mode. So when I look at this vibrational mode, I get very excited. The first thing we notice, there is leakage to the sides, right? And this is perhaps the reason why we get such low Q, 250. But there is also a very interesting thing to look at here. If you look closely, you will find that the waves are not propagating downward inside the substrate. They are only propagating laterally. And this kept me thinking for a long time, why does this happen? I have only a reflector on the top and nothing at the bottom. Why I don't get any waves propagating at the bottom? And then after lots of study, especially in terms of with the silicon photonics community, I figured out that I have built a phononic waveguide. And what we see here, we have basically the phononic crystal on top, and we have the bulk wafer at the bottom. And if we look at the dispersion characteristics of this structure, we will basically see the phononic crystal bands here, these two bands, and a very large band gap. And then we have the sound cone, which represents all the plane wave that can propagate into the bulk wafer. And we have this fractional band gap here with this localized modes confined between the phononic crystal and the bulk wafer. So we have constructed a waveguide, and the good news is we can control its characteristics. We can engineer this dispersion relation by controlling the dimension. So the structure I came up with, I said, okay, it's very easy now. I can have a main waveguide section here in the middle and have two terminations on both sides to prevent the waves from escaping laterally. So the final structure I converged to looks like this. We are only looking at the left half space, so the structure is symmetric about this axis. And we have here, this is the main phononic crystal waveguide section. And we have here the termination section. You will notice the different structure and period. And we use here fully differential driving MOS caps still, and a sensing MOSFET, as well as isolation. So this structure, everything seemed fine, and we expect to get very high Q after limiting the leakage of the wave. But there was a big challenge. Once you have a waveguide in solid material like that, and you start terminating it, you get two things. You get specular reflections, that's reflection normal to the incidence, but also you get scattering, which is radiation, or you can say it's coupling to other modes along several other directions. So the moment we basically terminate this waveguide here and add this isolation, we started finding leakage at this point. Basically, the wave started radiating in all directions. So in order to prevent this from happening, we basically need to match the dispersion characteristics of the waveguides. And unfortunately, we cannot do that without numerical optimization. So we started working on this, and as optimization, as an optimization parameter, I basically used the different dimensions of the different waveguide sections, as well as the isolation gate and the sensing FET. And of course, we can formulate this optimization problem as maximizing the resonator response, the transconductance, or maximizing the quality factor. And in this formulation, I don't need to say, or I don't need to state anything about matching waveguides. The optimizer itself will automatically take care of that, because this is the way to reach high quality factor. So we will focus only on maximizing the quality factor for this purpose. And once we started looking at that, the first challenge was, how do we simulate these structures? How do we get the quality factor of each structure? And the only answer was frequency domain FEM simulations. That's how we find it. But the problem with frequency domain FEM simulation is that as the optimizer changes the dimension, the resonance frequency keeps shifting. And this means I need to simulate a large enough bandwidth so I can always locate my peak as it shifts around. The second problem, I'm looking for high Q peaks, which means they will be very narrow. So not only I need a wide simulation band, I also need a very large number of points. And this is basically a recipe for very long FEM simulation. It took about 1 hour to simulate a single design. But when we think about that, the FEM solution, it basically provides a complete field solution at every point in the structure, meaning I get the displacement, stress, everything at every point at each frequency. And I don't really care about that. All what I care about is just the quality factor. I care about this transfer function. So this was a motivation to basically adopt model order reduction. And what's model order reduction? It's basically finding a very low order approximation to the transfer function that is very cheap to compute. We don't need to solve the whole system at all these frequency points. So the technique we used was Padé approximations. There are, of course, numerous techniques that can be implemented here. And Padé approximation is basically calculated around a certain frequency. In this case, we call it S node. And it's found by basically matching the Taylor expansion of the actual transfer function. So you can see here, for example, I'm calculating the Padé approximation around this frequency S node. And the blue curve represents my real transfer function, and the red curve represents the approximation. So you might think, this doesn't seem useful at all. It doesn't even capture the peak, which is why I'm doing all this work. But the good news is this approximation is very cheap to compute. It doesn't cost as much. And also, if you look closely, you will find it matches the transfer function in this flat region. So when looking at that, I say, okay, I don't need to simulate all these points. This can be 500 or 600 frequency points. I don't need to run FEM simulation for all of that. I only need to expand the transfer function around this point. But then what should I do about my peak? Very simple. I just keep moving the S node. I keep moving the expansion point. And at a certain time, I will basically hit the peak and I will find it, especially as this expansion is very cheap. So to make sure we always find the peak every time, There is a very fancy algorithm, and luckily for us, it's directly implemented in COMSOL, but few people know about it. And this algorithm basically implies Padé approximation to help you find transfer functions quickly. So how does this algorithm work? First, you start with an interval, in this case, our entire frequency interval, and then you find Padé approximation at the start and end. And what we do next, we basically compare the Padé approximation in between these 2 points in the interval. And in this case, they clearly don't match. So when we see that, we know there must be something in between. There must be a peak, there must be something happening. So the next step is basically bisect the interval and deal with each half individually. So when we do that, we repeat the process again. We evaluate Padé approximation at start and end. And in this case, for example, we find they perfectly match. So we know there is nothing in between. And we are done with that. And we keep repeating till we are done with all our intervals. So this algorithm is very powerful because it can basically move very quickly whenever we have flat regions in our transfer function. And we expect to have that since we have wide simulation bandwidths and we are looking for a single peak in this bandwidth. So this basically results in very fast simulation. Next, we ask the question, do we really need to simulate this wide bandwidth every time? And to answer this question, we look at a typical optimization run here. This is a very simple optimization run. The red curve basically represents the dimension that the optimizer is choosing. And the blue curve represents the change in the frequency here. So you notice as we approach convergence near the end, the dimension and the frequency doesn't change as much. And this will always happen with any optimization algorithm. And we also notice that the same thing happens here, and it can happen quite often during the course of optimization. So this basically motivated me to use memoization. And by memoization, I mean I store all the previous simulation results. And whenever the optimizer asks for a new design dimension, I go back and search for in all previous simulation till I find dimensions that are close to the new ones. And from these dimensions, I can estimate an upper bound on how much the frequency can change. And this can dramatically limit my frequency simulation bandwidth. So how do I estimate the upper bound? Well, we know that the wave equation basically transforms linearly under coordinate scaling. So if my dimensions change by 20%, there is no way that the resonance frequency can change by no more than 10%, especially in these bulk wave devices. This is very different from flexural modes or tuning forks or stuff like that. So this helped us reducing the simulation time even further. And also it's very helpful when it comes to evaluating the gradients by finite difference, because optimization algorithms, most of them will need gradients. So when using finite difference, we have this parameter epsilon that basically indicates by how much we change each dimension. And we set this parameter epsilon, so we can choose it to be very small. And also, we guarantee that the resonance frequency will not change more than epsilon times f node. So putting all of that together, this is how the complete optimization flow looks like. We have an optimizer running in MATLAB based on fbeancon, MATLAB function. It basically generates design points and asks to evaluate the objective function. And then we go do memoization search, check all the previous simulations. We select the simulation band and then perform COMSOL simulation with Padé approximation, calculate the objective function, save the state, and then move on. With this framework, we were basically able to achieve 40 times improvement in the optimization performance. And we can optimize the entire RBT structure, the entire unreleased RBT structure in less than 1 day, which otherwise would be infeasible without this framework. And we should also notice here, this framework is not really limited to resonators, because all what we are talking about is just some devices that require frequency domain simulation. It can be anything. It's not limited to this work. So it can be applicable to many other devices. So this is the simulation results from the final optimized RBT structure. And you can clearly see here the wave now is completely confined from all direction. It doesn't escape up in the phononic crystal, and of course down in the bulk wave in the bulk wafer by waveguiding, and also on the side here due to the termination. So we went ahead and implemented this this structure in IBM 32 nanometer SOI, and you can see here up there the full structure. We have the driving gate, sensing MOSFETs, and the driving gates on the other side. Everything is fully differential here, and we have the termination on both sides. And this is a closer look on the sensing FETs and the isolation gate. And the measurement results here, we got a quality factor of 11,600 at 3 gigahertz. So this marks 46 times improvement over the previous unreleased RBT generation. And we have to keep in mind, these devices, they don't require any release step or any post-processing. We just lay them out like you do with any other circuit or transistor, send them to the CMOS fab and get it, and that's it. And we are also insensitive to variation in the environment. We don't care about what is the pressure. We don't care about humidity. We don't have any such problems. The only thing that's remaining after optimizing the mechanical structure to get very good confinement is basically how to improve the amplitude of the transmission through this RBT, because the electrostatic driving that we are using and the piezoresistive sensing is not so good. So when we have looked at this problem, we found the only way to do now is to turn out to piezoelectric transduction. And we can do that through ferroelectric materials, which is currently introduced in multiple CMOS technology processes. They are mainly used for FE-RAMS technology. So we are now looking at basically global foundries technology, where they have a ferroelectric layer in their gate stack, and also a very well-established technology by TI from 2004, where they have dedicated ferroelectric capacitor in the first metal layer. So with this, I would like to come to the conclusion of this talk. We have basically seen that through the physical intuition and understanding of the waveguiding, we were able to select a structure that can confine the waves. And then we combine this physical intuition with numerical optimization to find the best dimension for the structure. And the result from both of these techniques, we basically got to impressive quality factor and F0 Q. And of course, the device size is very small, 13 micron by 4 micron. And finally, in order to improve the amplitude of the signal we get from this device, we are switching to ferroelectrics. And with this, I would like to thank all our sponsors and especially IFCS for their travel support. Thank you. We haven't looked at that, but for the temperature stability, I can tell you one thing. When we look closely at this structure, we find that the moded energy is basically stored in different materials. We have polysilicon, we have lots of silicon dioxide. So we expect that the temperature stability will be much better than using a single material, than using silicon on its own, for example. But we didn't quantify it in any way yet. The mechanical will basically, so for example, if you consider packaging, what will happen is that the entire device will get strained. And so we expect all these dimensions will look, after the strain, they will look slightly elongated. So we expect some shifting in the resonance frequency. But of course, this is something that can be calibrated for. Like beforehand, we can do a prototype, fabricate it, package it, and basically estimate the frequency drift due to the package. And then when we design, we know what will happen after packaging. Thank you. Yes. So in order to avoid that, what I do in this work in particular, my goal was to get the highest Q possible. So if my simulation finds multiple peaks, I will select the one that has the highest Q. And the second thing, I also introduce artificial damping to limit the quality factor, because the problem I saw is that lots of the times I will get very high Q peaks, like 20,000, 50,000 peaks, but these peaks are artificial. They are like some metal block that's resonating on its own, which doesn't make any sense. So with these techniques, I was able to basically get rid of these spurious modes when they appear. But again, the goal was to get the maximum Q possible. We can, of course, design to eliminate spurious modes. And in this case, we will basically, in the optimization objective function, we'll say, okay, maximize Q. And if there are spurious modes, just penalize this design. This design is bad, just keep it and move away to something else. Yeah. Yep. Yeah. So, yeah. So basically, I'm showing here only one device with one dimensions. But what we have done, we have fabricated multiple devices with different dimensions. And we found that their peaks correlates very well with the simulation. So this is how we know, okay, this peak in the middle, this is the one we are looking at. But the fact that the signal here is very small, so this electromechanical transconductance is on the order of 100 nanosiemens, which is really, really small, and the measurement of these devices are very difficult. So this is why you see all this noise, and it's not a clean curve like when you get with piezoelectric transduction. I have an estimation of the stress. The stress is on the order of around 10 megapascals at resonance.
Thank you very much.
Mm-hmm.
Very nice.